Herzlich willkommen. Mein Name ist Peter Palaga. Ich komme aus der Slowakei, wohne in Tschechien, spreche auch Deutsch, da ich einige Jahre in Berlin und Leipzig studiert und gearbeitet habe. Das alles ist aber gute 10 Jahre her und inzwischen hatte ich kaum Möglichkeiten, technisches Deutsch zu üben. Und daher werde ich den Rest dieses Talks lieber auf Englisch sprechen. So, I'm an engineer assigned to a product called Red Hat Fuse. Red Hat Fuse is basically the same code base as Apache Camel. It's a framework for integrating heterogeneous systems. I currently spend the most of my time in a project called Camel Quarkus. In this project, we are porting Camel components to Quarkus, which basically means creating Quarkus extensions. And that's my qualification for this talk. I'm using Quarkus daily. I'm writing Quarkus extensions, but I'm actually not the part of the core Quarkus team. This is what I'm doing at present. In the past, I was paid for fixing bugs in JBossDAP and Wildfly. In my free time, I like hacking in build tools such as source steps. Source steps allows you to declare your dependencies in terms of Git repositories and commits instead of released Maven artifacts. And I'm also a co-author of a parser for editor config files in Java. I also wrote a Maven plugin for checking and enforcing editor config for Java projects. A very simplified summary of this talk could be that it consists of an 8 milliseconds demo and 45 minutes of theory, what happened inside those 8 milliseconds. I hope the theory will not be boring for you, and I hope in the end you know what is Quarkus and you have a fairly good understanding of how it works internally. In the end, if we have enough time, I'll show you more of Quarkus, some interesting features, but it really depends on time. So let's start with the demo. I have compiled a simple project before this presentation. It takes about a minute. Where is it? Somewhere, I don't know. And I didn't want to bore you staring at Maven output, but what matters now is what the build has produced. And we can simply have a look into the target directory. And there's this file that has no extension. And it has no extension because it's a Linux executable, which can also be seen on the X permission here. I didn't want to do ls. I wanted to do lh because I want to show you that it's just 19 megabytes big or small. Okay? Because it's a native executable, I can simply start it like this. Have you seen how fast it was? Once again. And once again. Does it work? Yes, it works. Now, let's have a look how much memory it spends. And it spends about 18 megs of memory. which is quite nice for an application written in Java, right? So this was the motivation for you to get curious how this is possible. Sorry. So Quarkus, in the first place, is a toolkit. And it's a little bit of framework for writing Java, Kotlin, and Scala applications. When I say it's a toolkit in the first place, this is why. It enters your daily routine in form of Maven or Gradle plugin. The input for the plugin is the compiled Java code, either in form of class files or jar files. And the output is something we call here an optimized jar. This optimized jar can be run either on a stock JVM such as OpenJDK, or it can be passed to GraalVM for further processing, and the result is a native executable like the one we have seen in the introductory demo. This is very important in Quarkus. There are two modes. There is the JVM mode and the native mode. There are some advantages and disadvantages between those two, which we go through inside this talk. Okay? So when I said that it's a toolkit in the first place, you may ask, how the hell am I supposed to write my applications? And the answer is, Quarkus is embracing the existing standards, such as the good old Java-E standards like servlet, JAX-RS, JPA for persistence, CDI for dependency injection, bean validation, and transactions. And I think all of the new MicroProfile standards from fault tolerance, health, metrics, and so on. But also a couple of Spring de facto standards through compatibility layers. At the moment, Quarkus supports Spring dependency injection, Spring Web, and Spring Data. What the compatibility layer means is that the annotations from the respective Spring packages are mapped to some existing implementation inside Quarkus. So Spring DI is served by Arc, which is the CDI implementation. Spring Web is served, I think, by REST Easy, and Spring Data is mapped to Hibernate, I think. So the main idea is to make it easier for Spring developers to enter this world and to lower the barriers. I think probably not most of the features will work, but the most of the features will work. And if you find something not working, you should definitely file an issue. So except for the standards, there's a good support for many well-established libraries and frameworks, such as Vertex for reactive programming, Netty for lower-level network access, Apache Camel, where I work, for systems integration. There's an InfiniSpan client for accessing distributed cache. There's Caffeine for local cache. There's Keycloak for role-based authorization. There are extensions for generating Kubernetes and OpenShift resources. There's newly support for AWS Lambda and Azure Functions. You can read and write various kinds of documents using Apache Tika. You can search using Elasticsearch, and there is Cogito for business automation and some others that are not on this slide. Are you missing something? Yes, databases. So Quarkus offers support for the most SQL databases except for Oracle. Oracle wasn't available on Maven Central till recently, which is not the case anymore. If you need Oracle, you can Google and you will find an issue where there's a workaround described. So you can actually use Oracle applying some workarounds. So the list of databases here means that the JDBC drivers are supported. And for some of them, I think MySQL and Postgres, there are even Vertex reactive drivers available. So SQL databases is not everything we need. There's also Flyway for migrating schemas. There's support for Amazon DynamoDB, MongoDB, and Neo4j for graph databases. You can use both reactive and imperative styles of programming in a single application. The reactive is powered by Vertex. Quarkus was developed with the aim to offer as much developer joy as possible. And feature number one here is that it should be easy to start. So you can either use the Maven plugin to generate a project for you, or you can visit codequarkus.io and let it assemble a basic project for you. And you can choose here features or extensions that you need, and it will generate a zip for you that you can download and unzip. And open in your IDE. So when you look into it, into the POM, there's probably a thing that you would expect. It's a POM import that is there to manage the versions of your dependencies, because in the generator we have selected just a JAX-RS feature. We have just a REST easy runtime dependency here. I hope you can read it. Can you read it? Yeah, good. And there are two test dependencies there. There's just a single Java file there, which must look very familiar to you. If you ever wrote a JAX-RS endpoint, there's no difference on Wildfly or here. That's really the same file. And there's a development mode which you must try or must use when you are developing. You activate it through a special Maven goal, and it fails because I have not killed this one. So let's start it again. So it compiles the application and start your application at the background. And the Maven tooling, the Quarkus tooling, is still watching for the changes in your workspace. And once you change something, it hot deploys the changing into the running application, and you don't need to rebuild and redeploy manually. So let's try it. This one is still returning hello. Let's enlarge it. And I will change it to something more complicated. Let's take a configuration property from the MicroProfile specification. And let's have the default value hello. And let's create a field and let's return this field. I will now, so nothing happened here in the console. It happens when I reload. So it's recompiling and reloading the application when you hit the endpoint, which is interesting and actually nice that it works that fast. The same thing can be done for JMS and for Kafka and whichever kind of communication you have with your application. Let's do something different. This is actually a config property. This is supposed to be here. We don't have it here yet, and that's why the default value was taken. I will save. Nothing happened here in the console, and when I hit reload, it changes. Let's add an argument, and the annotation is query something, this one, and the name will be just name. String. Let's save it like this because I want to show you what happened if there's a compilation error. So I'll reload and it shows me the stack trace, I think, yes. Which is nice. Let's fix it and let's add a space plus name, save, reload. It gives me hello now because there's no name. France. Yeah, works. Perfect. This was the development mode. What else is there? Testing. There are special runners for JUnit, and they can be seen in here because the starter generator has produced these two test classes for me. This one is more important. Let's start it with that one. There's a special annotation that activates the JUnit runner. This one, Quarkus test, is for the JVM mode, for running tests in the JVM mode. It's better while developing because it's much faster. So let's kill the dev mode and ambient test, run the Surefire plugin, and it's gonna fail because we have changed what the application is returning. So I'll just change this to servus now and save, and it must pass now. And running the tests in the JVM mode takes a couple of seconds, which is fine. To test the native mode, there's a special runner called native image test, and you may choose to run the same tests in the native mode by simply extending the JVM mode class, right? And when I start this, it would be env and clean validate. And I have to activate the native profile. Not validate, verify, sorry. Native comp, and it will take about a minute. That was about the testing. Quarkus isolates you from the GraalVM CLI API. If you ever try to create a native executable using the GraalVM tooling, you will probably know that configuring all the options for the GraalVM native image command is all but simple. And Quarkus is shielding you very well from this. And as you have seen, running the tests, I have not done anything directly with the GraalVM tooling. Everything was done by the Quarkus plugin for me. And that's exactly what is happening here now. And it takes about a minute. And here in the Maven output, you can see all those options that this is passing to the GraalVM tooling. Good. There's also a Gradle plugin that I think is not as good as Maven, but if you hit limitations, you should definitely file an issue. You can choose from Java, Kotlin, and Scala, and actually the same holds for Kotlin and Scala, like Gradle. They are quite new, and you may find limitations that you should also report. Quarkus was designed with container first on mind. As you have seen, the native executable is quite small on disk, which allows us to produce small container images, which are faster to push and faster to deploy. You have seen the boot time of the native process, which is pretty nice, and that also maps to the deployment time of the whole container image. The memory is quite low, and let's have a look at the numbers. So you as Java developers surely know all the options you have for the JVM, like the heap space and so on. But in the world of containers, what matters is the RSS, the overall amount of RAM the given process is spending. And this is what you can set limits on in Kubernetes, and And PS minus O RSS is one way to output this matrix. So given this matrix, to compare Quarkus in the native mode and in the JVM mode, it's like this. The basic REST application will take like under 20 megs, compared with the JVM mode about 70 or 80. And compared with the traditional cloud native stack, it's like 10 times less here, right? And here, it doesn't matter if you take Spring Boot or Wildfly, it's about the same size. If you add JPA, the numbers are a little bit different, but you still get the idea where we go. Good. How about the boot time? It needs to be noted that the modern frameworks are cheating a little bit when booting, because they use lazy initialization and they report being started even before all the classes that are needed to handle requests are loaded. Okay, so what matters here is the matrix called time to first request. I'm not going to show how to measure it, but the idea is clear, right? That's the time needed from starting the process to the application being ready to serve the first request, right? And the time to serve the first request is not included. So Quarkus in the JVM mode is able to serve requests for a simple REST application under 20 milliseconds. On this laptop, for the application I have shown you at the beginning, it's 8 milliseconds. In the JVM mode, it's a bit more, but still much under a second. And with the traditional cloud-native stack, it's a couple of seconds. If you add JPA, and it strongly depends from the number of entities you have, it's going to be like 10 seconds, or tens of seconds maybe, with a traditional cloud-native stack. And it's still going to be about 55 milliseconds in the native mode, and like a couple of seconds in the JVM mode. Now let's have a look how it works. Let's have a look what the magic is that the Maven plugin is doing for us. So first, if you look at a traditional Java application server like Wildfly, or maybe the Jetty inside Spring Boot, or Tomcat, what they do during the boot, there are literally hundreds of classes that are run only during the boot. And they are not used later, and they are still occupying the memory. So this is not only time spent parsing configuration files. And if those configuration files are in XML, you need an XML parser. And maybe at runtime, you don't need an XML parser at all. And all those classes that are needed to parse XML are still there. That's quite a lot of space, right? Other things like class path scanning takes quite a lot of time to find all the annotations for persistence, for CDI, for whatever. You need to evaluate those annotations somehow, and you need to build a framework meta model for this. So if you are doing CDI, you must have some concept, some class for injection point, and some class for a bean that suits the given injection point. You need to warm up the reflection and maybe cache the fields of classes so that you don't need to go through all the fields each time you access them. And you need to open sockets to handle the network and start threads and so on. And the main trick Quarkus is applying is that it does the most, or as much as possible, of these things at build time. It's done once for every invocation that that happens later. And the output of this so-called build time boot is some recorded bytecode, right? That's the result of the magic. The recorded bytecode is starting the runtime services directly without scanning any configuration, because the configuration maybe doesn't change at runtime. And in this way, a lot of time is saved and a lot of memory is saved, because the classes are not there and they are not executed at runtime. So let's take CDI as an example. For CDI, you first need to go through the classes inside the application, and you need to identify all the injection points, and you need to identify all bean producers, and you need to decide which bean fits which injection point. Okay? And if you are doing this at build time, you can hard code the wiring into the boot sequence of the application. This is an example how you can imagine the process, but it's very strongly simplified, and this is rather a pseudocode than the real code that is there at runtime. So given that the user has these two beans in his application, the catalog bean that depends on the pricing bean, the CDI implementation in Quarkus can at build time produce some metadata, right? It knows that to create a catalog, one needs to inject the pricing into it through some create method that does something very similar like we do here for the catalog. And then it just puts this in form of bytecode, this is Java pseudocode, into the boot sequence of your application. And this is done inside a static initializer of a class, right? So you can see that even the pricing bean is instantiated there. And we will explain later why this is important. So a given extension can decide where to put that bytecode, that recording. It can either be put in a static initializer, as we have seen in the previous slide, or it can be put into a main method. And the difference is dictated by the GraalVM because it can do some further optimization with the code that is there in a static initializer. So this is the default, and things that we can't put into the static initializer are mainly things that access some resources that are there only at runtime, such as reading files and opening sockets, starting threads, and so on. So this is the architecture of the build-oriented container behind Quarkus. And the main part of it are the extensions. The extensions are units of Quarkus distribution. You are going to interact with them as dependencies inside your Maven project. So to use CDI, you will have to have a CDI dependency, but that one is default. You will not. That's not a good example. They configure, boot, and integrate some aspect of your application into a Quarkus application. So there is supposed to be an extension for a library or framework that you are going to use. And they prepare they make your application lighter to run on a JVM because they save some resources by the tricks that I shown before. And they make the code fit for the GraalVM, and I will show you later what this means. There's a whole ecosystem of these extensions already. And if you have an idea for an extension that you are missing, you should either try to implement it yourself, because it's not that hard, and there's a good guide how it can be done. Or you can file an issue on the GitHub project, and maybe somebody will implement it for you. Quarkus extensions are supposed to be, the specification is quite open, and it's possible to develop them as a third party independently from the main Quarkus project. And the project I'm working on, Camel Quarkus, is an example of that. We are not working directly inside Quarkus project, we are independent. And this is very good possible. right? And you can not only develop your extensions independently, you can also get included on code Quarkus.io with your third-party extension. If you look there, and this is just since a couple of days, there are camel extensions there, which are actually third-party. And those get included into the universe BOM that the generator is using here. So I could start using camel extensions here if I wanted. And those are actually third-party, not provided by the Quarkus core project. So the extensions are open. You are very welcome to bring your own. Now let's have a look at the native aspect of the whole thing. How much time do we have? Good. So the term Graal is a little bit overloaded. It can mean two distinct things. First, the Graal compiler that can be used either as an ahead-of-time compiler when creating the native image, or it can be used as a just-in-time compiler inside the stock JVM hotspot. For example, as a replacement for the default C2 compiler. Or GraalVM can be used, the term can be used as a name for this whole umbrella of distinct project producing this polyglot VM, right? And Quarkus is using just a small portion of the whole ecosystem. And in this presentation, when I say GraalVM, I just mean the Graal compiler used as an ahead-of-time compiler plus the substrate VM that is embedded inside the native executable. So when doing the ahead-of-time compilation with GraalVM, what it means? It means that you take classes from several sources. The first source is your own application. The second is the JDK API, the standard one. And the third one is the substrate VM. Substrate VM is something I'm not going too deep into. You can imagine substrate VM as basically containing a very basic garbage collector and some replacements for classes from the standard JDK that wouldn't work in the native mode. And the result is the native executable. Yes?
So during compile time only the required classes of the dependencies are put into the native executable?
Yes.
Okay, just to be sure.
Would be dynamic linking, so it's really putting them all into one executable.
Yes.
Okay.
So the native executable is actually linked against some C libraries, yeah. but not dynamically linked against any Java code.
Yeah, but this means all the code that you pack in.
Yes, we will.
You pack in
Yes, we will explain more what consequences this has. So what happens during that AOT compilation is lots of static analysis under this assumption that is called closed world assumption. Every single class, every single piece of code that is supposed to be running at runtime needs to be known at build time. This is a very strong limitation which has some nice and some ugly consequences. But the the nice consequence is that a lot of dead code elimination can happen. Because the compiler knows that it's safe to assume the closed world, it can eliminate lots of code because it knows it can come to the conclusion that some particular piece of code will never be executed at runtime. And it can throw away whole classes, fields, methods, or branches of if statements. If you work with the plain GraalVM, you would use the native image command and lots of options. And the output of it is the native executable. And now let's speak about the limitation. There's no dynamic class loading because of the closed world assumption. What it means? It means that it's not possible to implement a classical Java application server with this, because deploying wars and jars actually means loading classes dynamically. And this is not possible. There are JVM-TI and JMX are not available. What this means? There are no agents, JRebel, Byteman, no profilers, no tracers, and no Java debugger, because Java debugger is using those interfaces too. There's no bytecode, so there's no point for Java debugger to step in. It's native code. So the only option you have is to use a native debugger. But if you pay more for GraalVM Enterprise, that inserts these kind of symbols into the native code for you, you can even step through the Java code in the debugger. Okay? But this all holds only for the native mode. In the JVM mode, with Quarkus, all of those things work. Profilers, debuggers, and so on. There's no security manager. Does it matter? Probably not, because you are typically not going to run untrusted code, because all code is known at build time. There's no finalize. Does it matter? Probably not, because it doesn't matter anyway. There's no invoke dynamic and no method handles. Does it matter? Yes, because lambdas are implemented using invoke dynamic, and there's a replacement for them in the substrate VM, and they work as normal Java methods inside the native executable. Reflection is limited. You have to register classes and actually fields and methods and constructors for reflections. For reflection, if you know you will need them. And if you don't do this at build time, it's not going to work. And there's a special Quarkus option or annotation for that you can put there, and Quarkus will add the flex for you there if you need reflection. Similar holds for dynamic proxies, files, and so on that are supposed to be loaded at runtime. The same holds for JNI and unsafe and so on. Static initialization is very special. We have touched the topic when I was showing the CDI example, and I said that CDI in Quarkus can instantiate the beans inside the static initializer, and that it's default to put those things into static initializers, and this is the reason. Okay, because GraalVM can optimize those further And this is why the boot time is so fast. So the GraalVM tooling resolves all classes at build time. And this process of class loading and resolving dependencies is quite time consuming during the boot of a usual application server. So if this happens at build time, and if GraalVM applies this trick, that it takes the snapshot of the resulting memory and just puts it byte per byte into the native executable, the native executable, when run, doesn't need to do any class loading. It just loads the image, and the classes are simply there. That's why booting the native image takes just a couple of milliseconds. There's no class loading. The classes are bleep there, right? There's some downsides to it, and this is one of the main problems you hit when you go direction native image. That your framework or library that you are using is starting threads or is opening sockets and things like that, accessing files from a static initializer. So you either have to go to the project and fix it somehow there, or you have to apply some workarounds that are there also. You can mark some class as a class that needs to be that needs a delayed initialization.
But generally, you can start threads. It's just
you can start threads only from the main method, not from a static initializer. That's the problem.
okay.
So, and this is also a user experience limitation of GraalVM, that the CLI is so complex, and that Quarkus is shielding you from this completely. When speaking of limitations, this is something that could be called a limitation, but it's actually a trade-off, and you need to be aware of this. As I said, there's a garbage collector there in the native executable, right? As far as I know, there's no choice. There's just one. But there's no just-in-time compiler inside the native executable. All compilation happens at build time, and no further improvements are possible at build time, which is the case with classical, with stock JVMs, right? At build time, JVM is collecting some statistics and runs the just-in-time compiler based on those statistics, and is further able to improve the performance. And this is not the case with native executables and ahead-of-time compilation. So the result is that you get good startup speed with the native executable, that you get low memory footprint, you get a small size on disk, but peak throughput and latency are not as good, or typically not as good, as with the stock JVM. This is not a real scale, right? This is just figurative. And you should collect some real numbers on your use case, because this strongly depends on what you are doing inside your application. If you are doing some complex arithmetic operations, probably the difference will be important. But if you are doing stock or very simple REST endpoints, it will probably be negligible. Okay? Question?
That's only for the native image, or also for
AOT is equal to native and JIT is equal to JVM. So these are the trade-offs you need to know about. But there's a lot of development happening there in GraalVM and elsewhere, and this will probably change. So, and you may ask yourself, should I go native actually? Is it worth, because the peak performance and the throughput is not that good? And this is the answer, right? And it's called container density. If you deploy, you can deploy for the given amount of RAM and money in a public cloud, you can deploy just a small number of traditional Java app servers because they spend so much RAM. And public clouds, as far as I know, are the costs there are mostly driven by the RAM, okay? And if the native executable spends much less RAM, you are able to get much more power for the same amount of money, and as a consequence of that, for the same amount of money, you can handle much more requests here than here. Okay? That's the message. Good. What's the time? We have just a couple of minutes, so I'll probably just skip this. Okay, I'll show you just this one slide because this is probably interesting. So to produce the native image, you have two options. You either download the GraalVM from the Oracle website and install it locally and export the GraalVM home, and you use just the P or D native as a profile activation, or you can use Docker build that inside the Docker image downloads the right GraalVM version for you, and you don't need to care. But the limitation is that you have to be either on Linux or your target platform needs to be Linux when you are producing the containers, for example. Because if you do this, like I show here with this flag, it produces, even on Mac and Windows, the Linux native executable that you will not be able to run on Windows or Mac, right? But you will be able to produce a Linux container using that one. So, and let's go to the conclusion, because there's actually no more time. So, I hope you have understood that with Quarkus you are programming as usual. There's nothing new. You use Hibernate and JAX-RS and whatever you used so far. You just add the Maven plugin. It's good old Java. You are using standards and libraries that exists for edges, but you are getting much more power, much more performance with that. And you are actually reaching the efficiency level of Go. And there's one more little thing. Please turn off your phones and don't take pictures, because this is going to be announced on Devoxx in a couple of hours. Sorry. So Quarkus is driving full steam towards the version 1, right? And this is going to be announced today. And you didn't know, right? Because because I'll lose my job.
You're being filmed, right?
Good. You may want to follow Quarkus.io to hear the news today on Twitter. And you are welcome to retweet it too. If you have problems you think that are quite common, go to Stack Overflow. The Quarkus team is watching there for the Quarkus tag. Visit the guides and docs on Quarkus.io. The guides are very, very good, and even for writing the extensions. And I think that's it. Questions?
Can you tell something about build times, especially for big projects?
No. Try yourself.
Yeah. I think the thing is that if you have only a few libraries, as you did with the REST example, it's slightly straightforward, but it's straightforward for any compilation.
So the longest running integration test I have seen inside Camel Quarkus where I work were like 6 minutes. But what's the point of this information? You don't know how many and which libraries there were.
You make quick turnarounds on development. The time is summed up between the build time and the startup time.
You work in the JVM mode, which is fast. That's seconds. Okay. And when you are satisfied with the result in the JVM mode, you go native.
Fair point, yeah.
Do you have some tooling for the deployment in the cloud environment?
Yes, I have prepared the demo, but I put it away because there's no time anyway.
You can find it on the website? Or?
If you are interested, I can run the demo outside after the talk.
Okay. I think success of Quarkus much depends on the GraalVM, and so can you give a statement on what the Red Hat's commitment to GraalVM? So
that's the whole question, right? Yeah. Good. So the answer is that Red Hat is working towards providing a very good and satisfactory answer to this question soon. Red Hat is interesting to offer support for this, paid support, and the problem must be solved, right?
When you have a Java EE program and you take the approach of the wildfly, you can make several configurations, for example, security domains and security realms. How would Quarkus support such things?
So every extension exports some configuration options, right? And every configuration option is either build time or runtime. And things like this are supposedly being runtime, and you can change them. And if security domains exist there, I highly doubt. But some security options are surely there for role-based access and so on. And those must be runtime, so you can have several runtime configurations. And there's something called configuration profile, I think, in the application properties file, where you can have several ones in the same file, and you can activate them through a command line parameter. More questions?
Does it make sense to have a native image if you have a lot of configuration load on runtime?
Try yourself. No idea. Maybe, maybe not. Depends. And I'm going to publish the slides on my Twitter account, which is like this. Here. This is an older presentation about the Camel Quarkus, and I'll publish it today, probably. OK? That's it. Thank you very much.